don't know me, I'm Meghna. I am a second-year PhD student in Dr. Eden's lab, and I'm very excited to introduce our speakers for today, Charlie Andersen and Terry Scott from Burro. They're here to talk about their product and about building an autonomy business in agriculture. A little bit about the speakers. Charlie grew up on a farm, which led him to believe that tedious farm labor should be automated. He founded Burro after gaining experience with Case New Holland, John Deere's largest competitor, where he worked on special projects across sales, marketing, manufacturing, distribution, and autonomy mergers and acquisitions. He received his BA from Amherst College and an MBA from Harvard Business School. Terry, who's the CTO, he leads the development of a unified technical vision, architecture, and autonomy roadmap with Boro. Prior to Boro, he worked as a robotics software developer with Cozy. He received his PhD from University of Oxford's Robotic Institute, where his research focused on computer vision-based autonomous navigation and mapping. And it was my pleasure to work with both of them and the Boro team. Prior to starting my PhD here at Penn, we spent a lot of hot days working in vineyards and blueberry farms, getting these robots to work. And with that, I'm going to hand it over to Terry and Charlie.
Awesome. Well, thank you for the intro, Meghna. Much appreciated. So what we have pulled together is kind of just two parts. The first section is kind of what we're doing as a business, and we can go through that maybe in like 10 or 15 minutes, and then Terry will jump into what we're doing today that's kind of hard and like what's been hard along the way. And I guess if it's okay with you guys, I mean, feel free to jump in with questions, but we can also hold questions towards the end, unless people have like really, really burning ones as they come up. So if that's an okay way of organizing the talk. And so with that, so we as a team kind of see autonomy as a force for new market disruption that is poised to fundamentally change the future of how people work in the same way that PCs changed, offices in the 80s and 90s. And I think you might ask why now, or I think you guys are likely more aware of this even than myself, but I think you have this perfect storm of technology advances, especially around low cost computer vision. So the RealSense family of products coupled with good GPUs and low cost RTK GPS, and dexterity that's getting better and better, and more modular software and approaches to AI mean that suddenly you can build robots that can navigate pretty much anywhere, albeit perhaps not in a generalizable form, can recognize pretty much anything provided they're fed enough data, and then increasingly can tackle dexterity in more and more use cases. And at the same time, within agriculture, which is the world's largest industry, you have this increasing labor, it's almost like a sky is falling type situation, but it's actually a bit weird, or a bit real, where people that grow food in Western economies, so think like US, Australia, Europe, those types of areas, most of the workers that are doing labor on farms are comprised of immigrants. You've got a rising minimum wage, and the impact of that is that farmers are just simply running out of people to actually do work in the field. And I think when people think of farms, they tend to think of really heavily mechanized stuff like corn, wheat, soybeans, so things that are known as field crops. And the reality is that about 88% of the crop workforce works in unmechanized fruit, vegetable, and nursery crops, so all the stuff around the outside of a grocery store. And in those spaces, labor is typically about a quarter of revenue, and labor is the #1 challenge facing the space, and people are screaming for robots, but there's virtually nothing out there. And so into this, we've assembled a team that is devoted to bringing vision-based autonomy into the marketplace. And I think Meghna did an awesome job introducing our team. I think we are 13 at the moment. The only thing I'll add to this is we're in the midst of doubling. So we are definitely eager to talk with anybody kind of interested in what we're doing. And the approach we're taking is a bit different. It's actually, I think it's extremely obvious, but it's for whatever reason is a bit different than most of the approaches we see autonomy companies taking within ag. And so I think you'll see there's a whole host of companies working on high dexterity autonomy. So think things like autonomous strawberry picking, selective weeding, those types of approaches. And we are instead taking a stepped or a phased approach towards further autonomy, beginning with people scale collaborative robots that we can get into the marketplace today and that can build the base for more and more autonomy over time. And the problem that we are starting with is this exceedingly basic, obvious, pretty ubiquitous one. It's not an exciting problem in any way, but that's in part the appeal of it. And that is that when people are in very labor intensive crop production, they tend to do a lot of what you're seeing on the screen. So this is in Coachella, California, ambient temperatures around like 115 or 120 degrees Fahrenheit. Each one of those bins on board, and there are 4, weighs about like 35 to 40 pounds. And you've got 2 ladies walking up and down a row, carrying that weight rather than maneuvering it rather than doing the high dexterity part, which is the more valuable part. And so into this mix, we show up with something we call Burro. And you'll see some videos here. I'm gonna make sure I turn the audio off on this. But what this is it'll play. What these are small computer vision based platforms that fit where people work. I can get the thing to play. They fit where people work. And what they do is they use an approach to autonomy we developed called pop-up autonomy. And so with pop-up autonomy, instead of having like an iPad and something you deploy centrally, we've designed them in a way where everybody in the field becomes a user, and you can turn the thing on and train it over relatively short routes with it following you. And then it's able to build those routes into larger or longer and longer autonomous progressions. And as it does that, it's used today to carry fruit, but it's built in a way where with 12 cameras on board and it being online and pretty modular, we can, for one, ingest more and more data about the world around us that we can use to train better and better models on, both where to go, but also like what's taking place at the crop level. And so the thesis or the theory with this is that over time, we can expand it towards more and more autonomous tasks. And with that, I can go to the next slide. With that, I think to me, the reality when you're selling into ag is that if you don't have some sort of tangible economic-based initial value proposition, no matter how cool the tech is, you will really, really struggle to sell it. And so the initial value proposition that we bring is with a crew of 6 or 8 people running one of these things, each person becomes on the low end 10%, on the high end 40 to 50% more productive. And so you're able to offset the productivity of 1 to 2 people or more per day per robot, which is like an immediate 1 to 2 month ROI, just built off of that initial value proposition. And then separately, because of how we build these things, we're built in a way where we are inherently geared towards adding more expansive autonomy over time. And so again, because we have 12 cameras on board, plus sideways facing crop cameras, because we're built modularly, because the machines are online whenever they're running, we have a data pipeline that we can use to build more and more insights around crop health and kind of crop scouting, and then ultimately add the dexterity component so we have a product that can scale towards more and more autonomy in spaces where it's sorely needed. And so where we are today, I guess we were founded in 2017. The first 2 years for us were kind of murky. The first 2 years for us were like getting stuff working, like really, really hacking, trying to get a product that we could actually get that would go out into the field and work. And so we did 5 generations up until 2019 of machines. This past year, we received about 60 orders going into the spring, and we could only deliver about 1/3 of them because of COVID. And so where we are today is we've done commercial use with 8 customers over the entire year last year. We're through 7 generations of hardware, so we're now on the 7th generation of our product. We've done about 8,500 autonomous hours of operation over about like at least 15,000 hours. And we are at a point in time where we can have 5 or 6 robots running for every 1 person who's supporting them on the ground. And where we need to go next year, where we're going this year, is scaling towards north of 80 to 100 robots running. and then likely having one person on the ground from our team for every 15 or so robots running, which if you think about it, is a huge leap in terms of reliability, consistency, and then the more robots are running, the more variability they're encountering. And so therefore you've got to build them in a way that they can handle those, that inherent weirdness that which becomes more and more the norm. And then of course, longer term, our goal is pretty comprehensive automation. And then I think where we are commercially today, we've done paid trials in table grapes, blueberries, blackberries, raspberries, nursery crops, persimmons, and stone fruit. And we become really, really focused on table grapes. And so table grapes are a really, really weird crop. They're the ones you'd imagine, if you imagine like a Roman guy, lying on his back eating grapes, that's what a table grape is. They are all hand-picked. It's about a $3 billion crop. Half of that $3 billion goes to labor. So it's extremely labor intensive. And all of it is grown in like probably 5 or 6 counties in California. And so the appeal of it as robotics companies, we can be very, very focused on one use case, nail it there, move adjacently outside of that use case into others over time, and then sell and service directly initially. And on that note, the way we are selling these right now, I think if you guys are looking at other autonomy companies or startups especially, people throw out this term robots as a service quite a bit, or RaaS. And we have done a bit of that type of model. And the model that we have gone more and more towards is a SaaS model, or software as a service model, where you sell a piece of hardware initially at relatively slim margins, and then you try to generate a lot more recurring revenue out of your software as a service. And so this year, the deals that we have in place and the ones that we're building towards are like a 20% gross margin, give or take, on the hardware, and then something like a 50% gross margin on software. And we see that growing over time. And the other point to note is that we only sell these in 6 or 8 packs. We don't sell them individually. So every grower that we go after is someone who hires 2, 3, 4, 5,000 people every day to harvest fruit. And they're using using one of these for every 6 to 8 people in the field. So you're able to get some pretty critical scale pretty quickly. And then beyond this, the more exciting, I think we see this as the exciting thing, is that we are starting very specifically in a niche, but we can move upwards into that niche to add more and more capability around scouting and data, and ultimately higher dexterity. And we can also move horizontally into other use cases around the initial autonomy we're building. And beyond that, there's a platform opportunity where with something like this, we are democratizing access to an approach of moving from A to B with a people scale platform that anybody can operate, which is also modular and online. And so we think that over time, there are more and more expansive use cases that could emerge with a device like this, stemming from our initial use case. And that kind of said another way, if you imagine how something akin to Disney's WALL-E starts, actually as a commercial product, it probably starts as a vision-centric autonomous platform that works next to where most of the people within ag work. And over time, you layer more and more capabilities on top of that device until it becomes more and more general. And so with that, that's what we're doing on the commercial side. I think Terry can take you guys through some of the hard things that we're doing. And so Terry, I'll let you kick off that section if that works.
Yeah, sure. So I guess I'll begin by going through an evolution of like what we wanted and where we started. So in terms of Burro, so I joined in about 2018. The vision was really to build a robot that anyone could use that could go anywhere. And what we have today is something which does that, but then also has these additional layers, high fidelity perception, navigation, and brings on board a ton of data that we can actually use to improve stuff with. So onto the evolution. So the 7 generations of lessons. So on the left here, we can see sort of the very early prototypes, garage built, we built single devices at a time at that point. And it was really to generate interest. We wanted to build something that could showcase or get people interested in autonomy outdoors that people hadn't seen before, and that was really the purpose of it. and sort of like the use case for it was really emergent because we didn't have a clear idea of exactly how it would be used. Then sort of come into generation 3, then we have interest from table grape growers and blueberry growers. And what we have is this teach and repeat paradigm, where essentially you're teaching Burro how to navigate a particular route, and that's now you have these digital train tracks where you can navigate back and forth. The problem with that, very quickly we found, is that the routes that you tend to run go hundreds of feet, and in order to have that scale, we had to develop autonomous row navigation. And so what we do now with the pop-up autonomy is that we have a very short section where you can teach Burro how to navigate in a very unstructured environment. And now we can actually navigate down the road fully autonomously. So the setup time for this sort of thing is really minimal. So what we did last year was our first commercial variant. So we revamped the perception layer. So we made sure that we are safe around people. So I can take you a little bit through about that as well in a bit. And today we are aiming for many thousands of miles across many units. So already starting to scale and figure out how to support such a big fleet of robots, which is one of the major challenges for us this year. So here's an overview of our platform. So 4-wheel drive, we've got depth cameras all around. So you might be able to recognize we use RealSense, and along with all its USB issues as well. So we have 2 for an expanded field of view. They're just a really good device. So and so far the best option for us is to use 2 to increase the field of view. And so we get 8 miles of range, 4 horsepower. And so this allows us to go for a whole day on a charge while carrying a huge payload. And the reason for building something like this instead of maybe an off-the-shelf platform is because the off-the-shelf platform didn't actually exist. So you think of like a Husky, which doesn't come anywhere close to specs like this, or at the anything at the same kind of scale. So there was a large evolution there on the hardware. So as we go into scaling, what we really need to do is be able to measure what success is. And so we track this in something called miles per intervention, which is how far can we drive before Boro gets to this scenario that it doesn't know how to handle. So that would be an intervention. So early on, the miles per intervention didn't really matter. But now as Boro is a product, we're handing it to customers. It needs to be very, very hands-off. And so how do we track this? And how do we know what, I guess, miles per intervention is required to have one person support, let's say 15 units? And we got to about, what was the number we got to, Charlie? Last year?
You were like 7 or 8 towards the end of the year. I think
yeah.
it was 11 point something in November.
Yeah, so that was, we got to about that, which was somewhat manageable with one person for 6 units. And so we're aiming for sort of more like 20 miles per intervention to get that kind of scale. So that's kind of how we track it. And we track like all this meticulously through kind of online dashboard and the users report faults and that. So we have like pretty meticulous tracking on what goes wrong and where. So just an overview of kind of how we're set up to operate in table grapes. So we have Burro, which is outside in the avenue. The little green line is where you teach Burro how to move. And the blue line is where Burro knows how to do it by itself. And so as you stitch these things together, you have something which has very minimal setup time, and then can be autonomous for the duration of your pick. So that's how we're set up today. And so I think that there are a couple of videos that I guess Charlie could.
I think you remember the point that they're like, when you hand a device like this to somebody, they come up with like 8 billion different permutations of this flow. So like I think people tend to think this is really fixed, and the reality is like, the route can be, I don't know, 300 yards and it ends at a tent, or it can like be circular somewhere. So there's just a billion ways that people end up taking this initial flow and turning it into something that like we were at a point where people riff off of our stuff. And so you hand it to them, you're saying, hey, use it this way. And they end up using it some way entirely different, which can be a very, again, kind of a scary process as a company.
Yeah, and I think that's emergent out of this sort of teach and repeat that we've built into it, where you have, when you're outside of the row, you teach these little routes and you can really build up a flow, like any kind of flow that you want. And in terms of emergent use cases, that also allows us to demo something like nursery crops. So if we're towing trailers, then setting up a loop around a nursery is, takes a couple of minutes. It doesn't require an online dashboard. You're not setting GPS waypoints or anything like that. And so what this does is really showcase and figure out, like, okay, what is a different use case for us? What the challenges are that in order for us to then expand into this use case. So now we have a flow in nursery crops, and we have all the data. We now know all the edge cases and scenarios that we need to resolve in order to make that a viable product. All because we are able to set this autonomy up so quickly. So here's an example of someone learning how to train Burro. So I think she's just been told now how Burro operates. So right now she's teaching it how to get to a particular row. And then once Burro reaches that row, it's on its own.
And I feel like that part of the process looks so simple, but when you want to have like 1,000 different people do that consistently and repetitively, there's like a million little like weird operational problems that kind of come up with it.
Yeah. So I probably need to give a bit of context for this. So we see a number of challenges when trying to operate the robot like this. So we use a combination of vision and GPS. Now, each of those is good in different scenarios. So vision is really good to help us navigate down rows. We can pick up the row structure. GPS is really good when we're not inside the row, because GPS becomes totally unreliable as soon as you are under any kind of canopy of vegetation. And then so being able to kind of fuse those two things together and use the one when you don't have the other is crucial. And so what we illustrate here is kind of maybe just a simple graph of how we fuse some semantic information with GPS and vision. And so this is kind of just really the underpinnings of how we're navigating. We can move on. Yep. So the second part of the environment problem is seeing stuff. And so we've got a trained machine learning vision model that can really understand the scene around it. And this is taken from thousands of images across thousands of days. Well, maybe not thousands of days, but really hundreds of different environments. And so now we have this really meticulous understanding of the world. And that's been pretty crucial for our success. So here, Boro has stopped for a truck. And in this particular case, we know, well, that's a truck, we need to stop far away from it. And so the same thing is with people. So with this like multi-class model, we can actually behave differently around different obstacles. And so, for instance, we want to be much more conservative around trucks and people than we might want to be around, different types of vegetation. So this has its, so the drawbacks with this is that if you make certain assumptions about your environment, things can go wrong. So here, there are two failure cases we've outlined are one where Boro doesn't see the handle of a wheelbarrow. So our assumption there is that obstacles are of a certain size. Now where you have this like very thin thing out in front of you, that assumption is broken. And so now if we understand that we're seeing a wheelbarrow, we can stop really far away from it because we know there's a handle, even though we can't see it. And then the assumption on the right is that you don't expect obstacles over a certain height. Now you'd make that assumption because as you're navigating down your road, you all have this overhanging vegetation, which you want to ignore and drive through it. But as soon as you encounter a truck, that's something you want to stop for. So those are two edge cases that we kind of had to address on the fly. So this is a breakdown of where our issues lie and how we track it. So you can see that localization really being a predominant issue for us. And that's down to two things. One is the reliability of GPS, particularly as you have canopy interference, vegetation, that sort of thing. And the second one is the brittleness of a vision-based localization. So if you think, traditional visual features as landmarks and for visualizations, for visual navigation, we encounter so many changes over time, especially lighting, that tends to break, and then we just fall back to GPS. So that's just a big ongoing problem for us that we're working to address. So other environmental factors, heat. So if you look at a weather map of Coachella, if you go to the next slide, Charlie. This is fairly typical in Coachella Valley. So we frequently see the 3 digits, and we've completely had to redo our thermal solution for Burro to make sure our computing doesn't overheat for this year. We've got a couple of videos as well, which kind of show the challenges of the environment. So the first one is, here you've got really kind of overgrown vines, which is something that Boro still needs to navigate through. And so how do we detect whether that's something which is something we drive through or something that we should stop for? And then on the right-hand side, we have a big ditch with water, which Boro tends to handle, but it can pose some problems for us as well. So certainly a number of tricks in the environment. No problem. So moving away from navigation, if we assume that we have Boro, which is ubiquitous and is traversing the crop row, we can start to add this layer where we can actually do things like yield estimation. So here we've trained a computer vision model to identify clusters of grapes. And from this, we can get a fairly reasonable estimate of the volume of fruit that we can actually pull out at that time. This is super useful for growers, particularly if we want to track this over time. So one is, if pre-harvest, this allows us the grower to estimate how large the workforce needs to be in order to harvest the fruit. But then also over time, you can see the progress of a crop. So is it growing? How fast is it growing? When is it going to be ripe? And that sort of thing. And so the focus for us this year as well is really going to start adding these kind of layers. So this is a brief outline of where we are today. So we have this approach to pop-up autonomy where you can have Burro follows you where it follows you, and it can learn autonomous routes. It can navigate up and down crop rows, and it has this really good understanding of the world around it. And these guys are all cloud connected. So diagnostics are coming back constantly, so we can figure out what to improve. And so, as I was saying, the adding this data layer of what is called crop scouting. We're going to add the ability to scout rows autonomously, which means navigating from one row to the other. Currently, we're kind of fixed in this kind of teach repeat paradigm without really any path planning. And that's largely due to the constraints of the environment. Path planning is really hard, particularly when you haven't fully explored your area. And then building an online dashboard for GPS waypoints to enable things like nursery crop operation. So I think that's kind of the broad outline of where we're going with this currently. Yeah, and to recap, what Charlie said earlier is that to make all these kind of things happen, we need some extra people. So we're currently hiring.
So that's what we have pulled together. I guess, Terry, any other comments? I think that like hopefully gives people a decent idea of what we're doing. I think we can definitely go into more detail on things. I think we thought maybe kind of 30 minutes of what we have, and then we're happy to chat through any questions people might have, or we can drill down on more detail too. Yeah. So any questions maybe?
Well, I'll start. Are you guys seeing any competition in the field? Are there any competing companies?
Good question. I think I have a slide in here. This is my market map of companies in doing autonomy in ag. You'll see we're up here in this funky people scale platforms, and then we're doing it in kind of these crops at the moment. Candidly, we don't have any competitor right now that we're running into in the crops where we are that has anything even remotely identical to what we're doing. We do have a couple of people that are like at like a prototype level, might have raised like a couple $100,000 or like $500,000 or so. It might be at like generation 1. And so I think we feel reasonably confident that we will show pretty well relative to them. And then there's tons of money that of course is flowing into the autonomous strawberry harvesting space, and cherry tomatoes and some of those other areas, but we haven't seen any of that directly in our area yet. And then I perceive that this is a moving quickly type of a thing where you define a category, you move as fast as you possibly can, and at the same time your autonomy becomes better and better and better because you've seen all the weirdness in that space and incorporate it into your models of the world. And so a competitor that wanted to replicate what we're doing today would have to go through 6 or 7 generations, run them for 8,500 autonomous miles across a lot of different growers, have all of those lessons. I don't think you can sidestep that work entirely. So that at least is the hypothesis. Is Google or somebody else going to come into this tomorrow? Probably not in this exact use case, although they do have, I think in the case of Google, they have a project called Mineral, where they're trying to build carts that do data capture, but don't do any fundamental like farm job. And so that could be one example of a potential competitor in the next couple of years.
Yeah, cool. And I just wanted to make clear for the attendees, yeah, if you have a question, you can just unmute yourself and ask the question. We switched to a standard Zoom meeting, so yeah, feel free to do that.
Hey, Terry and Charlie, thanks for the presentation. Very interesting problem. And the more I talk with people who are doing robotics in particularly like vegetative environments, either in forests or ag environments like this, it becomes very clear that like navigation and localization is really hard because a lot of the paradigms around which vision-based localization works involves things being static. So I'm curious, how you guys have tried to tackle that challenge and where you see gaps in the research as far as what people in academia are focusing on versus what needs you find to work in practice.
Well, yeah, that's a super interesting question. I think that's kind of the question we ask ourselves all the time. So I think our approach has been to use pretty canonical approaches to visual-based localization. And that's kind of like the teach repeat paradigm that we started out with. Generally, that's insufficient. So what we found that you create this visual map, and within maybe half an hour, the sun has moved and those features are no longer relevant. So I think in terms of like what people are working on, they do seem to be tackling this problem in a bunch of different ways. So being able to update your map over time is one way of doing it. There's kind of recent research on like creating these deep features that are robust to illumination changes and perspective changes, which seems really interesting. So we tried a little bit of that last year, and so we had like limited success with it, and I think there's some issues with the way we've currently implemented it that didn't allow us to make full use of it. I think the one other way that we've got around this is what I guess you might call a semantic slam approach. Currently, we're using crop row detection as part of it to inform that as well. So basically, how can you detect landmarks without actually using kind of point-based features? Like, what other features can you use? For us, if we know that there's a road, then we can detect the center line of that road. That's a cool feature to use. So I think there are all these like little workaround approaches that have to add layers. I don't think there's one thing that's going to solve the problem. It's going to be 6 different things that eventually get to like full day visual localization from what we've seen.
And so I might have one other comment here. This not from a technical perspective at all, but I think in the investor and customer base world that you interact with as well, people assume that these problems are more solved than they might actually be. And so I think there's like people don't necessarily appreciate how difficult it is to remain localized all day long using vision outdoors with tons of people around. They assume that that's a solved problem because they see devices sometimes doing it in more constrained settings. So I think it's a double-edged sword, and that people assume it's easier than it actually is, and that's already been solved. And at the same time, you really, really need to solve it to get something like this working robustly all the time.
I think maybe even in academia, we think it's more solved than it is, particularly because of the lab kind of environments or, buildings around which, a lot of these algorithms are tested. I'm curious, so you are like very particular about saying vision-based SLAM. Is that because you guys aren't using any kind of geometric sensor? I know the RealSense has some capabilities there, but I'm curious if you aren't doing that, what the rationale was for that choice.
Yeah, so geometric sensors, so what are you thinking when you think of geometric sensor?
LiDARs.
LiDAR. Well, I think for LiDAR, in terms of solving some of the localization problem, you would need a 3D LiDAR. 2D, well, especially in vegetation, like you hit one leaf here and you've moved an inch and you hit a leaf back there. And so there's just isn't a lot of structure for you actually to register against. With the 3D LiDAR, that changes, but you're talking about a LiDAR that costs the same price as our entire unit. So I think cost is majorly prohibitive for using LiDAR. Yeah, so I presume cost is really the main reason for not using LiDAR. If you can use something like a Velodyne puck, if you had 2 of them, that would be awesome. But you just don't have a product if you use 2 LiDARs. So.
Yeah, I think that's frequently a question brought up. I think like a Velodyne puck, I think you can get like the 16 beam one for like $4,000 maybe right now. But the entire cost of our machine is $9,500. That includes like labor and assembly and everything else. So if we put 2 Velodyne pucks on there, we would be basically doubling our build cost. And you would need 2, presumably you would need one on the front and one on the back. So it would be economically kind of impossible for us to do.
Yeah.
So the other thing that you mentioned was that you're selling them in 6-packs. So at some point, would it make sense, or do you guys want these to communicate with each other while they're in the field? if like one robot stops working or is stuck somewhere, would the other one go and help it or take over its job?
Terry, you want to take that one, I guess, or?
Yeah, I think we've thought about that more generally, but like nothing specific as yet. I think so far there's no specific kind of problem or requirement for us to have that. I think like as we have more of these things running, I think we'll very quickly uncover, having a robot talk to another one to say, hey, this one's out of battery. I need to go in and cover it or something like that. It also requires like a very high degree of planning, which we just haven't had the resources to invest in. So certainly, like we're cloud connected, having like a little bit of a collaborative element, even like sharing maps between units. So I guess maybe like a simple step might be to, let's say you pull a robot out because it's out of battery, you want to switch another one in. You could just share the map via the cloud and just have it keep going. That might be kind of a simple step that we could implement fairly quickly. And so you switch the batteries on the other one and then get it going somewhere else.
I mean, I think the other comment to that, like in these types of environments, things move so quickly. So like people like move really, really quickly. Connectivity is really, really spotty. Like you've got a lot of water and grapes up high, so it's like hard to even like even getting stuff from reception consistently or communicating with an RTK base station somewhere. Like even those problems are quite difficult. And so imagining a robot consistently communicating with another and like saying, hey, go here, go there, in the event that another one went down or if they have to platoon, I think it's been kind of outside the realm of. It's been outside the realm of like possibility for us thus far. That's not to say there isn't some use case around it that we haven't thought of or could do at some point. And actually, sorry, and maybe the final point too is that as they are learning, like as we're pulling information off of them, we are pushing updated models that are from them collectively as well. So like in a way they are working together, but it's just not live into real time.
I had a quick question. Can you guys hear me, by the way?
Yeah.
Cool. So how do you guys deal with sort of like these terabytes of data that are coming in, especially when you're talking about sort of like that yield estimation model that you were talking about? Like, is that all being computed on edge, or are you like uploading these to the cloud or like some sort of manual upload to then run those models on?
Yeah. So I guess our perception model it's all run online, so it has to be. For the data streams, those can kind of be pushed selectively to our servers. So I think with the terabytes of data is what the robot processes. Then we have to figure out what is the right kind of data. So I think like one of our problems now is that we've got like 30 terabytes of data and like 90% of it is not valuable. so we certainly have to tackle the problem. It's like, how do you get valuable data from? You have to be like very selective about the data you want. And yeah, I think that's an ongoing challenge. So partly we have, if it's sort of diagnostic data, it's kind of incident. You report an incident, the robot then identifies that an incident has been reported. It then pulls the logs for that particular time frame and then uploads it. So from a diagnostics point of view, we can be very selective. And that also says, well, if we had an interaction with an obstacle, then use those images to feed into our training our model. So those are ways we'll be trying to be selective on data. If that kind of answers your question.
Yeah, I think specifically I was just interested about that grape yield estimation model that you were talking about.
Yeah.
So is that being computed on edge?
So that's not. I mean, it could be, but it's not. There isn't a need for it. So that data you tend to want to be able to use, let's say, by the end of the day. Like obviously a turnaround time of a week is not helpful. So you have your robots go through the field in a particular day. You pull off all the required data. You run it on a nice fast machine. Out pops like a map with measurements from different parts of the field.
Cool, thanks.
Yeah, Grant, I think you're hinting on something that's like it's a very basic fundamental difficulty with this stuff. I think there've been a number of companies have tried to do yield estimation in these crops, and they've tended to do it with like a TX2 and a couple of bastlers, and you like mount them on an ATV and drive them up and down every like fourth row. And that type of approach, you generate so much data that you cannot get it back to like a central thing to process it. And so I think there's a later, like the information we pull off at the moment with that type of stuff is kind of like R&D training models, that sort of thing. I think ultimately you would have to run natively on a robot like this to scale it, but we are not there commercially yet with these things on the crop data side.
I'm curious how you guys approach navigating in rows often crowded by human beings, and you know how the robot human interaction happens for Burro.
A lot of filtering. So I think the good thing about using crop row as a structure is that it's static, and so all the detections that you're getting of where the row center is, are estimating the same thing. So you tend to be fairly good at rejecting bad measurements. There are a couple of failure cases we've noted if you have a person walking in front of the robot, and so that person becomes like a constant, or becomes like a much larger portion of the scene than otherwise would be, and you can actually get a failure case like that.
I was thinking more about like, if you're working with someone in the way, you ask them to move, or maybe a person is walking in front of you and the robot wants to get by. I mean, is there any back and forth between the robot and the human at this phase?
Yeah, so that's a good question. So that goes to like user experience and kind of how do you communicate the robot state to the users. So currently it'll sit there and beep at you to get out the way, and sometimes people listen, sometimes people don't. It needs to be more like a foghorn.
Yeah, they get super annoyed on lunch break when it happens.
Yeah.
You'll see like a family and they're sitting down on lunch break and the robot's just sitting there beeping at them in a row. But it generally works. Terry, can you also touch on the end of road and how that's a hard problem? I think that's somewhat related to this question. Like why is an end of the row a hard problem?
Yeah,
it's something that seems incredibly simple, but
so for us, we've got, I guess, majorly a safety issue is that if for whatever reason Boro continues to navigate when it's outside of a row, let's say picking up like a box and a person and thinks that's part of the row structure, you tend to have instances where Boro is now in the way of traffic and is not handling that very well. So being able to say with 100% certainty that Burro is still in a row or not in a row is actually quite a difficult problem, because any kind of like edge cases you have at any point, it kind of like breaks the whole flow because you're making decisions of what Burro is meant to be doing at any kind of point of time. Yeah, I think we kind of just worked around that problem for the time being, but yeah.
And so said another way, rows tend to end in perpendicular highways. And so you'll have a robot that's going at like, a couple miles an hour. It gets to the end of the road, doesn't recognize the end of the road, goes out into the road, and there's a car whizzing by at 50 miles an hour. And so it's like something that like seems, so if you make your algorithm particularly selective and force it to say, I'm in a row for certain no matter what, then it will lose that it's in a row and not always make it all the way down the row. But if it's really loose and looking for a row all the time, you get into weird safety issues. So I think we have a lot of things like that where it's like getting it from 0 to 80% or 0 to 90% is pretty reasonable, but getting it from like 90 to 100% is incredibly complex or incredibly challenging with more and more users.
Hi. Yeah, I was wondering if the robot has any security features on it. Like if it ends up on another farm or gets stolen, does it get to communicate with the server, or how do you track it? How does it work?
Yeah, that's a good question. I think, to be honest, we've somewhat sidestepped that question by selling to people that we I guess not necessarily that we know, but I think we have a good idea of who our customers are and have a relationship with the customer. So I think if it gets stolen from then, I think that's a good question. I think maybe we haven't actually entirely addressed that, but so far we're GPS enabled and connects to the cloud. So if the robot is on, we can see where it is.
Yeah, and there's a lot of theft in these environments.
Yeah.
So you generally have people that go into the field at the end of the day and like steal copper valves out of irrigation pipes. And so we have a $17,000 or $18,000 robot all in that's sitting out there. I'm sure that we will deal with theft at some point, but it's also probably not the best asset to steal because it knows where it is and it's full of cameras. So I think there are two sides of that.
Could you talk a little bit? I guess I'm curious about how the workers view the robot. What kind of feedback have you gotten from them?
Yeah, Terry, can I address this one? Is that cool?
Yeah.
Yeah. So last year we had them in. Last year we had 20 units running. They probably were in something like 25 or 30 crews, and each crew is typically 50 to 60 people. So you're coming up on probably 1,000 people that have interacted with them at some level. In a table grape harvesting operation, you have a group of people that are picking and a group of people that are packing. And so the robot goes from a pack table to a row and then down a row to where people are picking. The pickers tend to really, really like these things because they're not wheelbarrowing at all. They just stand and they pick. And so they're more productive. They just pick. The packers, if they are men, tend to like it. And if they're little old ladies, which are pretty prevalent, they tend to not like it. And the reason little old ladies don't like it is because when this robot shows up, they have to unload 6 trays, each that weighs 30 or 40 pounds. Whereas before, if somebody showed up with a wheelbarrow, that person that showed up with a wheelbarrow would also unload it. And so there's an element of shifting work that they complain about, which we probably didn't think about going into it. And I think that can be addressed at some level. The best technique we've seen is just have, I know it sounds horrible, but if you have more men working in that role, the complaint goes away, or just has in our surveys. And then on the user end, a lot of the people that work in these harvesting environments, or there's a pretty broad spread of them. If you get into younger crews in particular, they tend to be enormously enthusiastic about it. When you're dealing with people that are like 75 or 80, which is actually pretty common, those people are sometimes less familiar with tech and can be a little bit, just a little bit like, hey, what is this thing? It's new. I've never seen it before. We have won over some of those people, but not all of them. So there's a strong element when you have a robot that's used by a crew of 6 or 8 people of getting them used to it, training them, having it work every time. So I think there's a gamut of feedback because we've had a lot of users with some complaints that we need to address and some that's been very positive. So I guess any other questions from people or comments? I think hopefully that gives you guys some idea of what we're up to.
I have a question, a clarifying question.
Yep.
To what extent can the robot deviate from these paths that it is trained in particular the ones going to the rows? Like if there's something in the way, I saw that they stop. Is there a way that they can deviate and return to the path that they were trained?
Terry, it would be very nice if we did have that.
Yeah, we're actively working on that. So being able to plan around different obstacles. I think it depends on how far from the path you are. Especially if you rely on something like vision, then going off the path and coming back, being able to plan around something is almost impossible because you need to be pretty much on the path you've mapped. Otherwise, you won't be able to localize. But since we're using GPS, that becomes much more viable to do. So yeah, certainly in progress.
Yeah. I think that highlights too, like, I think like vision gets super, super brittle. And so you, as soon as you start being really, really flexible with a route, you lose localization. And then also the more you deviate from a route, the more likely you're going to go into a situation where you shouldn't go and therefore are likely to hit something. And so I think it becomes like those types of questions become more and more complicated when you get out into these kind of cluttered settings where, in these cluttered settings where you've got like stuff, people, boxes, wheelbarrows, all these kind of funky things floating around that are moving really, really quickly. And then you start talking about a lot of movement. So we've really, really narrowly scoped stuff thus far and are trying to figure out how to be a little bit more flexible with something as seemingly simple as that, which is actually very, very complicated in a real-time production environment.
I see.
Yeah. Yeah. I guess I could put a question back. Does anything about like what we're doing seem like people have like a solution for that we're kind of missing? You know, like we've kind of heads down trying to figure out solutions to like hard problems, and you don't always know like if, you know, we're not always up to date on, you know, the research and what the state of the art and a lot of this stuff is. So I mean, do these kind of problems align with what's happening in research, or are they interesting? Something to think about as well.
I can speak to that a little. A lot of research work that is going on with, say, visual navigation happens in much more constrained settings. One of the most popular benchmarks is like the Habitat Challenge, which is a simulator of indoor buildings, houses and stuff. So having like this kind of dynamic outdoor environment with less rigid boundaries seems like a much more challenging problem than a lot of what we've faced so far. So we'd definitely be interested in expanding to this, but I'm not sure of anything that can like solve this off the shelf right now.
You hear me?
Yeah, thanks for the reply.
Sorry, you guys hear me?
Yeah, we can hear you.
All right, sorry, my mic wasn't working a second ago. The other suggestion I would have is there is a research group I know who's working on similar problems. So there's the Autonomous Mobile Robotics Lab at UT Austin. They are currently working with the Jackal deployed outdoors. They're using stereo vision, and they're trying to deal with this problem of dynamicism in the environment, where over multiple days you have different like cars parked places. So knowing whether you should localize them or not, and then also dealing with things like foliage. Right, they're not actually deploying in like canopied areas to the same extent you guys are, but they still are dealing with some of the similar problems of not having visual similarity. In particular, they are focusing very heavily on the localization aspects.
Yeah, it definitely seems to be a theme that many people are trying to tackle, particularly on the kind of the driverless car front. This sort of notion of lifelong autonomy. So I think like, how do you navigate through day and night, through seasons, that sort of thing. I think we're trying to constrain it to like, can we do this over the course of 2 hours instead of a whole day? That would be a huge leap from, let's say, the half an hour that we get now. So.
I think people also tend to be constrained in some ways in their research to which data sets exist and which ones are easy to use. So right. If you want a bunch of researchers piling on this problem, you could release some data. You'll probably get some.
It's not a bad idea. Yeah.
Terry, why not? I think we totally could, right?
We've got terabytes of the stuff. Yeah.
Yeah.
Yeah. I think like the criteria for data sets can be quite stringent. So depending on what you need to actually work on. So if you're working on navigation, it'd be good to have like some kind of ground truth that you can actually benchmark something on. So I guess we haven't like necessarily focused on collecting data sets that can be used for benchmarking, but probably as we go into testing the season, that'll become more of a focus. And so likely we could actually plan to have something like that available. So if someone is interested in doing something like that, let us know. We can actually plan to have the right sorts of data available sort of later in the year.
Yeah, I think I just wanted to jump in. I think this is a terrific idea. The problem with data sets for navigation is that, I mean, there aren't really that many as far as I know. So if you have anything that's remotely usable, although I guess in your particular case, we won't be able to use your hardware unless unless we work at Burro.
We have some extra ones floating around that could also potentially be solved. So okay. It's not prohibitive.
Yeah, I think that could be quite useful. Yeah, if the data set has the right structure and and it's usable.
Awesome. Yeah. No.
Yeah. Okay, so I think this was a great chat. Does anybody have any final questions? Cool. If no, yeah, this was much more free-form than our usual seminars. I hope everybody liked it. I hope it was useful for people. And yeah, thanks a lot to Charlie and Terry for the very nice presentation about this company. This was very interesting.
Yeah, thank you for having us.
Yeah, thank you very much. Really appreciate it. So awesome. So cool. Well, thank you very much. And yeah, I guess on our end, if people want to learn anything else, just shoot us an email or check us out online. And if you want to check out a robot in person, let us know too. All right.
Yeah.
Awesome. So
yeah. Thanks everybody for coming then.
Yeah, thank you. Bye-bye.
Bye.
Bye.